In this video, we're going to focus on something called a reaction mechanism. This is a series of steps, we're going to call them elementary steps, that get us from reactants to products. Here's the deal. The balanced equation is a good thing. It tells us what the reactants are, what products are formed. It tells us the ratio by which reactants react and products are formed. We can get good information from the balanced equation. But it doesn't really tell us how we get from reactants to products. That's like this magic that occurs on the arrow. How do these molecules form products? We understand that there's probably some kind of breaking bonds and rearranging atoms to make new products. But what's really happening in that gray area between reactants and products? That's what a mechanism is going to try to explain. It's a series of steps that hopefully get us from the reactants to the products. For example, we might have this balanced equation. Nitrogen dioxide reacts with carbon monoxide to produce nitrogen monoxide and carbon dioxide gas. Now, this could occur in one step, or another proposal, another mechanism, is that maybe this reaction occurs in two steps. What if, in the first step, two molecules of nitrogen dioxide react to form nitrogen trioxide and the nitrogen monoxide? Now, this is a good thing. I want this nitrogen monoxide on the product side. So maybe here's kind of this elementary step that gives us one of the products. What if then I take that nitrogen trioxide and react that with the carbon monoxide and produce nitrogen dioxide and carbon dioxide gas? Here's another product. I want this. Okay, so here's my two products. Watch what happens when we put this all together. I'm initially reacting two molecules of nitrogen dioxide, but do you see in the second step we actually form one? We can kind of cancel these. In the long run, I want to look at a sum of all the reactant particles and all the product particles. I'm reacting two nitrogen dioxide, but I form one in the second step. So what if we cancel one? Cancel this, cancel that. In my overall balanced equation, I only had one molecule or 1 mole of that nitrogen dioxide. Now I also have that in my balanced equation. Now look at this other goofball, NO3. Do you see how it's formed in the first step, but then the second step reacts it, we consume it? We can cancel that. I form NO3, but then I use it up in the second step. So it's not going to show in my final equation. The other reactant that I do want, that is right here, the carbon monoxide. So if you add these two intermediate steps, or elementary steps they're sometimes called, we can cancel like terms. Anything that shows on both sides of the equation, whether it's in the first step or the second step, and we should get the overall balanced equation. But now what's interesting about this mechanism is there are some particles formed and consumed that do not show in the overall balanced equation. For example, that NO3, that is nowhere in the overall balanced equation. It's formed and consumed. We call that an intermediate. And it's just that. It's something that's formed in an early step, but then it's consumed in a later step of your mechanism. So it's not really going to show in the overall balanced equation. Now, these mechanisms, it's important to note, it's a proposal. Nobody really knows exactly what's happening during that arrow. exactly how do we get from reactants to products? I don't know. We can't see it on like an atomic level. The best we can do is propose these mechanisms. And what we'll kind of find in these next few videos is that, we can look at a proposed mechanism and we can evaluate it and say, yeah, that's a logical mechanism. That would get me from reactants to products. This is a possibility. Or we can deny it and say, well, no, this is unlikely. This would not likely get me from reactants to the desired products. But there could be more than one proposed mechanism that could be appropriate. And that we'll never know exactly which one is the best. All we can do is propose these mechanisms and say, yeah, that's a possibility. That gets me from reactants to products. Does it occur in 1 step, 2 steps, 3 steps? That we'll never really know. But there are ways that we can, again, deny ones that are unlikely. And that's kind of what we're getting at with these reaction mechanisms. Okay, so from this first slide, that's an important vocab term down at the bottom. We'll kind of come back to that in a little bit. Intermediates are things that don't show up in the overall balanced equation. They're formed in an early step, but then they're used up in a later step. How we use the term elementary step then, that's all these individual reactions that if we add them together and cancel like terms, we should get the overall balanced equation. If we don't, we would deny that mechanism. We would say, nope, this doesn't get me from reactants to the desired products. And it's got to show up in like the right ratio from the overall balanced equation. We can describe these elementary steps by what's called molecularity. Oh boy, it seems like a fake word, doesn't it? Molecularity. It just refers to the number of particles or species that have to collide on the reactant side in order to produce the reaction of your elementary step, of your little mini reaction. So molecularity, it really does just refer to the amount of particles that have to collide to make the reaction occur. If you only have one reactant particle, we call it unimolecular. And so maybe this would be like a decomposition of some sort. Unimolecular, there's just one reactant molecule. Or we could say like 1 mole of particles. Bimolecular, there are 2. Teramolecular, there are 3. And here's kind of what happens. I mean, can we have more than 3 reactants? Absolutely. But now here's this gray area where if we propose an elementary step that has more than 3 reactant molecules that all need to like simultaneously collide, it becomes kind of unlikely. And we'll kind of look at some examples of this in class, but to kind of see how, if I have 2 reactant molecules and obviously they need to collide to get the reaction to occur, sure, that might happen. They also need to collide in the proper orientation. So if I have like polar molecules, they have to collide with the partial positive next to the partial negative. But do you kind of see how, like, if we start adding in like 4, 5, 6 reactants that all need to simultaneously collide together at the same time in the same place with the proper orientation, the chances of that all coming together is pretty slim. So that's one thing that we kind of look at when we're evaluating a mechanism. If we have elementary steps that really do have too many reactant particles, we might deny that mechanism and say, that's kind of unlikely. So what we kind of mentioned here, this is important. This is kind of a big deal. When particles collide, we say that collisions must be effective. An effective collision means, number 1, the particles collided in the proper orientation. So again, a good example might be like polar molecules, where they might need to collide partial positive to partial negative. If they're coming toward each other like partial positive to partial positive, there probably is no collision. They'll repel each other. So the particles need to collide with the proper orientation. They also need to collide with enough energy to make a reaction occur. I mean, they can't just putt-putt bang into each other and and not really form a reaction because there was no energy. Now they really need to commit to this collision. They need to collide with the proper amount of energy in order to break the bonds on the reactant side and have those atoms then available to rearrange and form new products. If they don't collide with enough energy to break the bonds of the reactants, nothing happens. We say it's not an effective collision. They might collide, but there's no reaction that takes place. These are important. Kinetics is all about, getting those reactions to occur, studying the rate at which they occur, and how we can change that. Well, these are the two things that have to happen in order for those collisions to produce a reaction. Proper orientation of the particles, of the reactants, and they have to collide with sufficient energy to make that reaction occur. So we'll kind of use these factors as we start evaluating proposed mechanisms for a particular reaction.